Alright, time for another draftphysics.com, debatephysics.com also. But again, well, sometimes the debate is worth having because at least we all learn something. So, like when Ian Gosling found that you can actually buy a spring that's overcompressed, that is, the coils are really pushing on each other. They're not relaxed when you're holding the spring. So, it's already got compression in it. And that's sort of important. It sort of relates to this other experiment by Disbar. And the fact is that I'll correct an error I made in reading what he wrote. Okay. So, but it doesn't really matter because it still demonstrates a catastrophic mistake somewhere. So, besides my mistake, this little mistake. So this 7 is actually a 1. Okay, so I read it wrong. Now the problem is here when you correct this. Okay, so it was pointed out by the 321 guy that I made this error, and then he started doing. See, that comes out to 1.4. Well, you can't use the 1.4 argument when the velocities aren't changing. See, the two theories disagree only when you change the velocity. Okay, if they have the same velocity, then the two theories say it should be double or triple or whatever the amount is. Now, yeah, they don't have the same numbers because of the 1/2 mv squared, but clearly you're going to end up with the same proportions. So now you're in trouble because instead of doubling, you doubled the mass. All right, and now instead of having 4.4 here, okay, now you have 3.1, which isn't even close. That 3.7 wasn't all that close to 4.4 either. Okay, but clearly 3.1 is nowhere close. So obviously you got a problem with the 3.1, okay, having the 0.9 here. Okay, so now you have 0.9, and then you have what is it, 6? 3.7, no, 1.1. Okay, 1.1. That's it. That's too high an increase too. Oh, it's 8.5. Yeah, sorry. So yeah, it's 1 to 85, so that's 65. Yeah. No, it's 75. 0.75. Okay. Seems high for some reason. Anyway, so 0.9, 0.75, and then 0.55 is the increase. Okay, but the point is that automatically there's something wrong here. Okay, with this first number, because these numbers, this has to be, okay, by both theories, this has to be twice. This has to be 4.4. Because you just changed the mass. The 1/2 mv squared still has mv in it, okay? And if all you're changing is the mass, then you can't be doing this exponential part. Doesn't have any effect. Doesn't make any difference to the end result number. You're going to get the same doubling for this. We're supposed to agree on what happens when you double the mass. Well, we should agree on what happens when you quadruple the mass also then. Yeah, so I just saying, clearly no conservation of momentum, and I guess I could just make the logical argument that there's, no one's making the argument that gravity gives disproportional amounts of energy. So if I put a 1 mass on the scale and I get a number, and I put a 2 mass on the scale, I get twice the number. The scale is measuring linearly. So obviously the rubber band, who knows? Now the fact is that he does pre-compress the rubber band, so I didn't think of that before. But that should be having the opposite effect. That should make the 2.2 number go way down, because he has to first uncompress the rubber band. That is, deal with the fact that he's already put pressure on the rubber band, and that's like having an extra. Well, yeah, so it would have the opposite effect. That's like putting a weight on the rubber band. Right? The compressed spring. See, well, this is interesting. All right, so let's go over it. So I was going to take down the video, but I'm saying, okay, the rest of the video is accurate. The fact that his other experiment was, in fact, an inadvertent proof of my point, because clearly he did it so badly. And all that's true. This diagram here that was in the previous video. The fact that he put the weight here, okay, a much higher center of mass, and then claimed he got these same results. Okay, so huge error. All right, so in the Gosling case, we have a spring, all right, that's pre-compressed. That is, the coils are right next to each other, and they're pushing on each other. So it's already got pressure in it. So when you put a weight on it, the weight, the first weight wasn't even enough to make this spring uncompress much. So it wasn't enough energy to even start the coil separating. So he wasn't getting much for the first pound he put on. Not much was happening to the spring. So obviously, you're going to distort your results because you have to uncompress the pre-compressed spring. Now in this case, it's as if, okay, he had placed a weight on the scale previously. That is because he's already stretched the rubber band. So the scale is already reading, an extra plus number because he's already pulled, okay, on the rubber band, giving it extra compression. And so the rubber band's already stretched. So this first number is a distortion on the scale. So it's like readjusting a scale. So the 0 isn't 0, right? They put an adjuster on here. Somewhere. I guess it's inside this hole. So you can adjust the scale, to compensate for any kind of irregularity that might make your 0 not 0. Okay, so the 0 is supposed to be 0. It's supposed to start at 0. So what he's essentially doing is starting here and then doing the experiment. So the first number is exaggerated more because of that extra, okay, that gets added to it. So that's the problem here, is that by overstretching the rubber band, it's the opposite of the Gosling effect. We'll call it that. Yeah, the Gosling effect. Where he's pre-stretched the rubber band, so the first number is way higher than it's supposed to be. And so obviously if it was more like 1.1, then the answer of 4.4, right, for the 4 mass would be perfectly consistent. But regardless, there's obviously, let's see, 1.1 would not be 3.1 for doubling. So we know that the answer, if we take the 3.1 number and we say that's twice, it's closer to it. It still has the distortion in it, but let's just say we're trying to figure out what the distortion is. Then the 1.5 would be closer to what the spring should have read when he did the 1 mass. So I'm just trying to, so when he did a 1 mass at 2 velocity, the number was 4 point something. And so that's been, you can argue, distorted by the compression, the pre-compression of the spring. So we're still, I wouldn't think that would be enough to account for that big a difference. So we can go back to the hammer experiment, like I said. So the previous video is perfectly valid in that it points out that when he did the experiment with a heavier, stiffer lever, but he put the weights in the wrong place. Clearly in that experiment, if he got the same results as he got in this experiment, demonstrating some equality between the 4 mass at 1 velocity and the 1 mass at 4 velocity, that you could clearly understand that the two can't be equal if he has the weights in the wrong places. So I'm just saying, he's still stuck disproving his own experiment that already previously proved it. And I could go back to the Brozo experiment with the lever and launching the billiard balls and just point out that 19 to 11 is pretty close to 2 to 1. All right, let's see what else we need. I mean, that's not explicitly a 4 mass going. I mean, the lever would be a good place to do this experiment. 4 mass going 1 velocity and a 1 mass going 4 velocity. I mean, 2 velocity. Clearly, it won't work on a lever. So you can't put those two things on the opposite side of a lever and get it to wobble. It won't do that. The 4 mass will win decidedly. So there's still really good reason for people not to be confused by these nonsense experiments that really aren't credible. And part of the credibility is that first you have to prove that your device you're using to measure your scale. First you have to prove that your scale is linear and that it actually can measure 2, 3, 4, 5, 6. They can get those numbers right. If they can't get those numbers right, then there's no point in turning your scale and doing this. Okay, there's no point in doing impact experiments with your scale if your scale can't measure the weights correctly. And the argument is that your scale can't measure the weights correctly because you have it poorly calibrated, because you have overstretched the spring and all the numbers are now wrong. All right, so do I need to say more? Well, I'll pause and see if there's more to say. So I was wrong. I mean, 3, 1, 7. I mean, it's it's a problem with our language that obviously 3. I mean, 1s and 7s shouldn't look anything like each other, frankly. And the fact is that you can draw a bad 7 that looks like a 1, and you can draw a bad 1 that looks like a 7. But anyway, it's still my bad. I can't, frankly. Listening to some of his content is very difficult because he's such an obnoxious, lying sack of shit. So often I'll just watch, and so my bad for that. But still, it doesn't really matter because both theories say twice the mass, twice the energy. So the fact that those two numbers don't match is a big problem. 3, 2, 1 guy. You can't use the 1.4 argument. Doubling the mass is not supposed to give you a 1.4 change in the energy. Okay, it's supposed to still be twice the energy. Okay. All right, just trying to think. This shouldn't be that hard to explain. I mean, if I drop one object that weighs 2 mass, okay, and I drop it, it's the same thing, right? There's absolutely no way to convert it into anything other than dropping 2 1 masses right beside each other, right? So I drop 2 1 masses right beside each other. Okay, it's the same as the 2 mass. So if the scale reads 2 for something, like something weighs a 2, okay, it can't have a secret amount of energy, okay, because it's these 2 objects that it's really made out of. And one of them can't be worth 3 energies and one of them only worth 1 energy. I can't move the scale 1 unit, okay, of distance and say, well, this object did the 1 unit and this second unit that's worth 3 energies, right? This is only 1 energy here. Okay, you only get 1 energy here, right? So the first thing that hits somehow produces 1 energy and the second one hits and it somehow produces 3 energies. You can't say that the 2 mark on the scale really equals 4 energies, all right? Because I just break it into 2 objects, and you're saying the 2 objects, one of them can't be 3. It can only be a 1 and a 1. It's only 2 units of energy, okay? This was 1 unit of energy. I could drop 1, and I get a 1 on the scale, and now I have a 2 on the scale, and the 2 on the scale can't mean, oh yeah, well, secretly one of these is 3. And certainly both of them can't be, what would the option be? But that secretly this 1 was really a 2 and this is a 2? I mean, they both have twice the energy somehow when I put them next to each other, that now they're double the energy? How can I double the energy when how can I mean quadruple the energy when, go from, what should be 2 to a 4 instead? what you're saying is secretly a 4. 2 is really secretly 4 energies. So again, how can you do that? How could I just split the mass in 2, have 2 separate things falling, and how can you claim, well, now I'm going to have 4x the energy, when this one only has 1 energy on the scale, this one only has 1 energy when I drop it on the scale. So I drop these independently of each other, and they only have 1 and 1. And then somehow you're saying when I drop them together, I have 4? Come on. I'm saying that I think that's an undefendable position, frankly. I think it's just absolute nonsense that there's any way, because you really, again, you can't say that they both got an increase. So somehow the second one hitting somehow produces 3 units of energy when it's exactly the same momentum, same pressure, same force. And somehow, magically, the rubber band says, I'm going to hide that fact. I'm going to do something inconsistent with Hooke's law and demonstrate that pressure isn't proportional. So you either accept that if you've properly configured your spring, your measuring device, that you should get consistent results with Hooke's law. And you're not. Alright, so I just thought of an experiment that probably should have been done by physics, right? Because this would all be very helpful if all this stuff had already been done the way it should have to prove all of these different points. I was thinking about this rubber band, and the fact is it's a variable spring, right? So depending on how stretched, how far I stretch the rubber band, I potentially get very different results, right? So if I stretch the rubber band a little bit, okay, now I use it as a scale. That's the interesting thing to figure out, right? Is how does it measure mass? Does it measure the masses differently? So one would have the expectation that, say, if I put a mass on this one, that it will stretch further, okay, than if I put it on the tighter one. It'll stretch less. I mean, that would be my intuitional expectation. Okay, something like that. But we don't have that experiment, so we don't really know what happens when you change how stretched the spring, the rubber band is, what its spring constant is, right? Its stiffness, as it would be called, I guess. And so that's the advantage of rubber bands. So the simple thing to do is to put a 1 mass on the rubber band at this way and see if the 1 and the 2 create the same distance and obey Hooke's law, and therefore have some meaning as a scale, or whether in both cases you end up with that. That is, so that even if you tighten the rubber band, do you get the same Hooke's law? Does it obey Hooke's law? Do I get twice the compression for twice the weight? So that'll tell you a lot about how rubber bands work in reference to Hooke's law, and whether you can use the stretch of a rubber band to measure energy consistently. Right, so that's simple enough, right? That's not that hard an experiment to do, right? Put a stretch of rubber band in gravity, put a known mass on, double the mass, and see if it obeys Hooke's law, right? Not too much, not too demanding. And the more you stretch the rubber band, does it break the rubber band's ability to measure proportionally, to obey Hooke's law, to be useful as a scale. All right, that's probably enough.